And I'd just like to begin by thanking everybody for the invitation to come here, because I think localization landscape is a very interesting topic and approach, and one we are very interested in core. And it's very nice also to get an opportunity to give an overview of some of our work on atomistic modelling of electronic structure of nitrides. I also thank some of the earlier speakers, Claude in particular, that your talk sets up background for some of this very nicely. So in the presentation, what I want to do is begin with an overview of the motivation for the impacts of order and disorder in 3-nitride heterostructures, and then look at ways to model them. And you saw before lunch people using density functional theory, and we use it in also density functional theory specialist technique, how the HSE approach to do supercell calculations on a range of materials. I'll take an example actually from a different area of germanium carbide to show how small supercell calculations can give you misleading electronic properties. Then move on to what you can learn from larger supercell calculations on indium aluminium nitride and indium gallium nitride, and kind of the empirical atomistic approaches that allow us to treat up to 100,000 atoms to get an overview of the properties. So the 3N motivation I don't really need to cover, I hope, after Claude's talk, but I think the important thing to say is that gallium nitride and indium nitride and aluminium nitride are very different materials. They've got 10% mismatch, lattice mismatch, and that has impact on the electronic properties. They also, as we've discussed, got these large built-in electric fields due to both the spontaneous polarization effect, where there's built-in dipole naturally in the material, and a strain-induced 1 piezoelectric, which adds to that as well. And these built-in polarization potentials lead to the band edges, having that spatial dependence, as we have seen in the picture here. That can be overcome by growing on non-polar and semi-polar indium gallium substrates, in that with gallium nitride, if you grow on a non-polar substrate, as the polarization field is now within the plane, there's no discontinuity going from one layer to the other, and so consequently that leads to elimination of the polarization fields in such structures of potential benefit for LED devices. And then one of the big drivers behind simulation and modelling of 3-nitride materials is that although nitride LEDs are wonderful devices, nevertheless they all suffer from something called droop, whereas you increase the drive current, the efficiency starts to drop off. And work to try to eliminate the droop and understand what causes it is one of the major drivers, I think, behind a lot of the work on nitrides, and that if that can be eliminated, their efficiency can be sent even higher. Now, going back to what nitrides are not, if you look at semiconductor materials like gallium arsenide or silicon, as Claude had, they've got wonderful periodic structure that goes on, and then we can, as a result, plot the band structure using Bloch's theorem, where we can associate a plane wave vector k with each state, and then because of the periodic boundary conditions, there's a maximum value. The maximum k value in a 1D structure with period L is pi upon L. So if you know what that actually also means for later in my presentation, if I double or treble the size of a supercell I'm looking at, then the maximum wave vector will go down by a factor of 2 or 3 as well. So there is and in terms of the overall band structure as well, k equals 0 is the gamma point at the center of the Brillouin zone in both these cases, and then two of the most important other high symmetry values are at L, which is along the 1, 1, 1 direction, and at X. In materials like gallium arsenide or aluminium gallium arsenide, properties actually vary close to linearly with composition, and so the virtual crystal approximation has a long history of being used to analyze 3-5 semiconductors, and it actually works very well. And using the envelope function method as Claude described, you can look at a gallium arsenide, aluminium arsenide quantum wild structure where you have confinement of electrons given by the blue state there and holes given by the red state, and actually as a description it works very well. If you look at the best gallium arsenide, aluminium arsenide quantum wilds at low temperature, the exciton line width is less than an MeV. There's I think half an MeV in this particular case, so virtual crystal, really describing the material very well. I should say before moving to the next slide that the scale here is 40 milli-electron volts, because the next slide shows the equivalent data for 3 nitride alloys, and on the picture you can see the lines are just as narrow as I've drawn them, except in this case we're going over a range of 1800 MeV, and in this case a range of 800 MeV. So actually the intrinsic broadening in C-plane and M-plane quantum wells, very broad, large intrinsic broadening of the optical, of the photoluminescence spectra, and that's indicative of very strong disorder in the two materials. Now, as Claude also mentioned, if you look at data from on the atomic distribution of the structures, you see a random alloy distribution. I mean, some of the early ideas was if you get that width broadening in a spectrum, it's because maybe compositions are different in different places. Consequently, that there's kind of some correlations, and consequently, different regions having different band gaps contributes to the broadening. But I think it's now widely accepted, no, there's a random distribution there, and the randomness on its own is sufficient to give the observed distribution. And this brings a problem when you come to modeling indium gallium nitride quantum wells, because if you think of, simulation for devices is very, very sophisticated, probably as sophisticated as FIFA. You can see I made this slide originally 2 years ago, you can tell. That's what the simulation can really do as nicely as FIFA, but the problem is dilute nitrides, actually the nitrides are actually not working on working in a very disordered pitch, and that's what needs to be addressed. Pardon?
It's more rugby.
I come back to some rugby later, yes. Actually, I won't come. Sorry, speaking as an Irishman to a Frenchman, I won't come back to rugby later. But so, in order then to understand the importance of these disorder effects, we kind of undertake work at different length scales, multi-scale simulation. For devices, you like to have a continuum model. But very often it's more than I've seen in earlier talks using first principle approaches. The continuum can treat nanometers, microns. First principles calculations only deal typically with up to about an order of 100 atoms. In some cases, maybe you can push it a bit further. But the interesting length scales are between the two of those. And so we've developed empirical atomistic approaches to treat the intermediate length scales. And doing it, starting, say, with, from hybrid density functional theory calculations, you can calculate structural and electronic properties of materials. Based on the structural properties, then get accurate valence force field models describing them. Based on the electronic properties, deriving an empirical atomistic type binding model where you put effectively a set of empirical orbitals on each atom and then calculate the self-energies and hopping integrals between those different orbitals to give you the band structure. And using that then allows you to treat, as long as it's well benchmarked, allows you to treat structures, say, on the scale of 100,000 atoms or so, for instance. And the importance of that length scale is important. I want to begin with an example of showing how small supercells can mislead occasionally, taking the example of germanium carbide. And the interesting thing about germanium as a group 4 semiconductor is that it's almost direct gap. The lowest conduction state is actually at the L point, which is about 150 MeV below the gamma point. So you only need to tweak the band structure slightly to make a direct gap. And you can make it, and it's been shown recently that adding tin will do that for you, bring you, to a band structure which is a narrower gap but is direct gap. And it's been proposed recently that carbon might also do so. Sorry, I'll skip that one. And with the carbon, if you do a 128 atom supercell calculation of germanium and then of germanium carbon, well, first of all, because of 128 atoms, states that where at L and X fold back to the zone center. So the black dots here show you the band structure of germanium, and the lowest conduction state is 4 degenerate L states folded back, with the gamma state then about 150 MeV higher. do the calculation of 128 atom germanium, 127 atoms germanium, 1 carbon, and it looks like you get a direct band gap semiconductor. And if you look more, and you can check that by trying to unfold the band structure, which is work out if we would go back to trying to get it back to the going for the 2-atom supercell. And you can see again that in this case it does give rise to what looks like a direct gap below, at the conduction band minimum. And if you look at individual eigenstates, you see the lowest conduction state is one with large charge density around the, partly localized around the carbon atom, and looking very much like a perturbed conduction band edge state in this direct gap semiconductor. However, if you want to look at larger structures, what we do is we develop empirical type binding methods where we take the constituent materials that we want to look at, in this case germanium and carbon and a fictional zinc blende material, germanium carbide, in order to look at interactions between germanium and carbon, calculate with the solid lines the band structure using density functional theory with the HSE functional, and then with the dashed lines calculate the band structure using type binding method. And you can see you can get a good fit to the overall electronic structure, in particularly near the direct gap, which is the energy region you're interested in, and then you can also ensure the parameters are appropriate by ensuring they have correct strain dependence present, and therefore that your model will also treat local bond stretching and bond angle bending. And if we now look at the type binding analysis of germanium carbide, you can see on the left-hand picture there is the band structure of 128 atom germanium, again with the 4 L states folded into the zone center and the gamma state just above it. Next to it is the band structure of the supercell with 1 carbon atom. And if we look at the character of the lowest states in this structure, yes, it looks direct gap, but if you look, you will see that the character is predominantly L-like with a small amount of gamma mixed in. We can then also, however, the nice thing with the type binding model, you can go to larger structures. So then we went to 2000 atoms, or 1728 atom structures, and in each case now we can calculate the electronic structure in each of the disordered structures. In the case of germanium, and what plot here is where the germanium gamma and L character goes. So in the very left-hand figure, you can see L yellow at the bottom of the conduction band, green germanium at a higher value, and then as you start to induce disorder, you see doing many 25 randomly disordered calculations in each case, you start to see a distribution of energy states, and also that the bottom lowest states remaining predominantly L-like with little gamma weight. So what actually going then from the ordered 128 atom calculation to the disordered structures, what instead you see, instead of the direct gap, you see a distribution of carbon states below the germanium conduction band edge. I should just introduce briefly the inverse participation ratio, which was mentioned earlier this morning, as defined by integrating the 4th power of the wave function at every point over the volume of a structure. And the idea is that if you've got a delocalized state, as here, for instance, with 7 lattice sites, then with equal weight on each of those sites, the IPR value is 7 times root 1 over 7 to the power of 4, so it's actually 1 over 7, or 1 over the number of atoms in the structure, being a highly delocalized state in this case, whereas a localized state, if it's sitting just on 1 orbital, then is an IPR of 1. So the larger the IPR value, sorry, that's the participation at the, so the larger the IPR value, then the more localized the state is. And if we now do calculations on the different, look at the different disordered germanium carbon structures, what you find is with an explicit analysis, you see band mixing and disorder effects. You see in each different calculation, the lowest conduction state has a different energy, and that whereas the IPR values in germanium for the gamma and L states are close to 1, that by the time you get to the germanium carbon, the values are going up to 100, or by the time you get to the largest structure, even as large as 150 in these calculations, normalized to the, well, times 1 over the number of atoms. So clearly what you're getting instead of a direct gap material, as it would have been expected, is germanium with the distribution of states in the band gap. And that is not unlike actually what happens in gallium phosphide nitride, where when you, again, gallium phosphide is indirect gap, introducing nitrogen introduces a distribution of localized states below the conduction band edge, as illustrated from this paper from the 1960s of different luminescence bands in gallium phosphide nitride. Now, in this analogy, gallium phosphide nitride was actually the original green LED, which was did give green light, but as you can see, just about visible in the phone here. So that actually, well, our conclusion then would be for germanium carbide is that likewise it may well be a luminescent active material, but it will be to other direct gap materials as gallium phosphide nitride is to 3 nitrides, in other words, not very efficient. So on the other hand, if we now move to larger supercell calculations, in this case I want to focus on indium aluminium nitride, which is one of the, the least widely used of the 3 nitride alloys, but still very useful and potentially useful in a number of different cases. And in this case, the motivation is that it really extends the spectral range over which you can get direct gap emission. It actually covers from deep in the infrared for an indium nitride up to deep UV for aluminium nitride, which is an energy gap of 6 eV, well into the infrared. It's also lattice matched to gallium nitride, so it offers the possibility, for instance, of growing in super lattice structures, lattice matched, which can be very useful for Bragg mirrors in vertical cavity lasers, and also because it gives you an extra degree of freedom, it gives you the possibility of polarization matching in heterostructures. So again, it sounds very useful, is potentially very useful, but has a significant issue as a material, which is the band gap bowing is very strong in this material. And I've plotted there a combination of both theoretical and experimental results showing how the energy gap varies with composition. In case you can't see how strong the bowing is, that line shows you what would be the equivalent of a linear variation. And that strong bowing is very critical for a wide range of potential applications. In particular, it means that aluminium indium nitride gap actually approaches that of aluminium gallium nitride, lattice matched gallium nitride, very quickly. And so aluminium indium nitride AlGaAs has interesting band lineups and relative energy behaviors. But the question I want to address is the origin of the strong bowing in this material. And the origin can partly be explained using approaches like localization and landscape theory, but also goes beyond that, I think, for some of the explanation. And when you see strong bowing materials, very often an approach to explain it is what's called the band anti-crossing model, which is if you have something like gallium arsenide, if you create the alloy gallium arsenide nitride, straight line shows how you'd expect the energy gap to vary with composition, whereas the dots show theoretical variation, which match very well the experimental variation in the ranges where gallium arsenide nitride has been grown. And what you're seeing is a very strong bowing in this case, and the origin of it is that nitrogen actually is sufficiently different from arsenic that it introduces a defect state in the conduction band, but a resonance state above the conduction band minimum. And then as you increase the composition, those nitrogen states interact with the band edge and push it down, and that's described by a band anti-crossing interaction between the nitrogen states and the conduction band edge. And that band anti-crossing model, for instance, would not come out of localization landscape, because the localized state is effectively associated with higher conduction bands that would not be included in the localization landscape. This is actually one of the first examples of a cation-based localized state in a group 3,5 alloy. And then it's interesting to follow further how does the conduction band and valence band evolve with composition in aluminium nitride. And to do that, because aluminium and nitrogen are both in the top row of the periodic table, local density approximation can actually go quite readily to supercells containing about 1,600 atoms. And while LDA is the problem that it has reduces the energy gap, when you're starting with an energy gap of 6 eV and it's reduced to 4 or 5, then you can live with that. And what our calculations showed was that if you put one indium into a 1600 atom aluminium indium nitride supercell, it gave rise to the lowest conduction state being very much localized around the indium site, and the next conduction state in the 1600 atom case also being localized there. So effectively what we're looking at is hybridization between a localized state and the conduction band edge, and that hybridization being described by a band anti-crossing model, where the lowest conduction state is then a combination of what was the original delocalized state interacting with the localized indium related state. And if you do the calculations then more accurately using HSE, where however you're restricted to much smaller supercells, I think of the order of maybe 1 or 200, I forget the exact number, again you see the lowest conduction state has the same behavior, but it does, as it turns out in this case, the next state in the HSE, because this different environment, is not so clearly seen as being the localized state. But in that case, we believe therefore that an aluminium indium nitride, because indium is so different from aluminium, it actually creates localized states in the conduction band that interact with the aluminium nitride conduction band, pushing it downwards. And scales here, of course, are quite different, but that band anti-crossing model then describes well the evolution of the conduction band edge energy with indium composition for a range of different structures. What we're looking at here are ordered structures, random structures, and clustered structures. So you can, for instance, get 128 atom supercell with 2 indiums next to each other, has the same indium composition as a 64 atom supercell with 1 indium in it. And we can, however, if you compare the calculated valence band edge energy in the different cases, you can see always that if you've got 2 indium atoms close together, if you've got clustering, that you get the valence band edges pushed up due to the presence of the 2 indiums close to each other. Now this, I think, can be partly is consistent with the localization landscape behavior. It's because things are just getting, you've got a deeper potential around the indium site. And that shows, for instance, if you just put 1 indium into a supercell, compared to putting 2 indiums nearest neighbors, and what the data here is plotting is the calculated probability density for the highest valence state in the 2 cases. So weak indication of some localization effects for the single indium, a much stronger localization when you start got pairs. And this is again just kind of underpinning how randomness leads to broadening of the band edge spectrum. So in order to model that on a larger scale, for the 3 nitride wurtzite materials, it turns out we've been able to develop a tight binding model using just an sp3 basis, which is 1 s electron, 1 s state, and 3 p states on each site. And you can see that around the energy gap region there, that the tight binding and DFT are in very good agreement with each other in terms of the description of the band structure. So but that was one aspect of the benchmarking. We can benchmark in that way, and again treat effects of strain and deformations directly in the calculations. And what we found is that using the tight binding model is partly validated by the fact that it provides good agreement, including with experiment and with more sophisticated data for the band gap bowing across all 3 alloys. In addition, for the 3 nitride materials to do kind of detailed local behavior, it's also important to realize the built-in polarization field depends on both spontaneous polarization and strain-induced polarization. And strain may vary locally, will vary locally in an alloy between different positions. So we therefore derived a local polarization model where you treat directly the effects of strain locally. And in the local polarization model, we then benchmarked it by comparison against Berry phase calculations on 128, on both on ordered and on random structures, in terms of how the total polarization of the structure varies based on the distortions that are included in the Berry phase calculations and in the wider ones, and got very good agreement for the overall macroscopic polarization of the structures we were looking at, showing that the local polarization model then should give a good description of what's happening on a local scale, which cannot be looked at exactly from the Berry phase calculations. So, and when we do that, for instance, if you then look at what does the potential look like in a non-polar quantum well structure. So here we have an indium gallium nitride quantum well with gallium nitride barriers behind it, and it's M plane, so that the polarization vector is lying in the plane, but you can see significant fluctuations in the potential there due to the local polarization, with brightest yellow being polarization potential of about 80 MeV, going down in the greens and blues to one of minus 80 MeV. So there's quite a local impact of local polarization fluctuations on the overall properties as well. Using the type binding model for the aluminium indium nitride, it then describes well the observed band vector Boeing observed experimentally, giving you both the conduction band and giving you an indication of how that Boeing splits between the conduction and the valence band, and also gives you very interesting, confirmation of the value of the model comes from looking at the optical properties of aluminium indium nitride, because in three nitride materials, there are three highest valence states made up of px, py, and pz orbitals. So they have x, y, and z symmetry, and when they're recombining with an s-like electron, they would then emit light that's polarized either in the x, y, or z direction. In aluminium nitride, the Z-like state is about 250 MeV above the X and Y ones. So it always emits light that's polarized vertically with respect to a quantum well direction. And that is actually very poor for LEDs, because if you want light coming out of the surface, you want the emission in the plane of the quantum well, which is called TE polarized. In indium nitride and gallium nitride, the situation is reversed, and the crystal field splitting as the X and Y state sitting above the Z, and by about 50 MeV in the case of indium nitride. So if you took a virtual crystal model and say, where would you expect aluminium indium nitride to switch from TM polarization to TE polarization, you'd say you need about 90% indium for that to happen. However, if you do the calculations taking account of local disorder effects, we find that the highest valence states switch from being predominantly Z-like, which is the blue dots here, to X and Y-like by an indium content of about 20% due to localization on the indium. And actually, that's also the point where the transition occurs experimentally. So wave function localization near the indium sites really then leads to this dramatic change in the polarization characteristics of the device, which is certainly of potential benefit if you're looking at creating optical emitters that would be emitting from the surface. And I think also that what I like about a result like that is that it is a benchmarking that the atomistic model is describing well the impact of the localization in the structure. So now, if we move, also by the way, so just to comment one thing that's related to localization landscape, in solving HU equals 1, it's effectively a single band model. It's just a single parabola, whereas here at the top of the valence bands you have 3 bands, and I think for transport that the localization landscape probably is sufficient to describe the effects of 3 bands using 1. For optical properties, there are challenges there, for instance. Moving on to then indium gallium nitride, where we have again developed type binding models to look at the structures. So if again looking at the optical recombination, what's interesting if you compare optical recombination in C-plane structures, which is where the polarization field is along the growth direction, and in M-plane where it's in the quantum well, then in the case of C-plane, the observed photoluminescence has a non-exponential decay. There's not a single time constant describing it, And that can be understood, if you presume that you're looking in the C-plane case at separately localized electrons and holes. Whereas in the M-plane case, where the polarization, macroscopic polarization vector is within the plane, so there's no built-in field across the quantum wells, the PL is observed to decay exponentially across the spectrum, and that can be understood if the excitons are becoming localized in that case. So the question then is that how would that fit in with an atomistic analysis of the two types of material? So in order to do that, we've calculated, we can set up supercells. We set them up with about 100,000 atoms, 80,000, and with dimensions that are about 10 by 9 in the plane and 10 vertically, with a well width of about 3.5 nanometers. So you've got about 30,000 atoms therefore in the quantum well in a simulation such as this. So if you've got 10% indium, you've got about 3,000 indium atoms distributed at random in the quantum well region. And then what we do is, for fixed indium content, we just put in atoms at random and see how the properties evolve. And we can directly inspect the hole and the electron wave functions, and we can calculate the inverse participation ratio for the electrons and holes, as in those structures as well, to look in detail at the local properties. So first thing here is, if we look at the variation in electron and hole ground state transition energies across 20 different calculations, and I think this was 10% in GAN quantum well, and what you can see is across 20 different calculations, a wide spread in the energies. Now in our calculations, we find that the spread in hole energies is far larger than that in electron energies, with a spread there between just 20 different random configurations of up to about 200 MeV, whereas in the electron case, the spread is more of the order of 10 or 20 MeV. Now, if you want to know I think you probably can guess what the origin is, but if you then look at different structures, what we find is that with the electrons, which have a lower mass, in an envelope function approximation, and therefore you might expect to be more delocalized, they are. That if we look at if we take a single example of the electron ground state in a quantum well structure, where we include a well width fluctuation, then the electron state is sitting very much in the well width fluctuation. It's spread over the whole region, whereas by contrast, the hole state in each of the random calculations we do tends to be very much, the highest hole state is very much localized in a particular region of space. So highly localized holes, the electrons behaving largely as you would expect from a continuum model. And if we now do say, but that's treating the electrons and holes as independent of each other, so ignoring the Coulomb attraction that you'd expect between them. If we now turn on those many-body effects interactions between the electrons and holes, what you see is that the picture hardly changes at all, because the electron and hole were localized in separate regions of space. They remain largely with the same energies and wave function distributions. And if we now see how that impact, for instance, on the optical properties, then work which my colleague in Tyndall, Stephen Schultz, has carried out with Phil Dawson's and Rachel Oliver and Colin Humphrey's groups, we're looking at the PL peak energy dependence on excitation energy. Now, you can see that if you start out and you excite above a critical energy, the PL peak energy you measure remains approximately constant as a function of excitation energy. But as you go below a certain point, there's a strong redshift of the PL energy as you go below that critical energy. And this is, we'd expect, and as we can show, is consistent with carrier localization effects at the lower energies. And if you now look at the inverse participation ratios for the electrons and holes across different configurations, this time instead of plotted as a function of configuration number, plotting IPR as a function of the configuration energy, and normalizing to the electron IPR for the calculations of the lowest conduction band energy. you can see that the electron IPRs actually do not change very much in the different structures we're looking at. The electrons tend to have the IPR goes down to about maybe 0.6 of the maximum IPR in over the range of structures considered. Whereas for the holes, if you look at the IPR values, first of all, they're much larger because the holes are much more localized. And secondly, as you get to structures where the highest hole state is at higher energy, so the most localized states, the IPR values shoot up compared to the other values. So you can kind of say up to a certain point you might argue, maybe these are largely, there's a definite transition here. And so overall, then how does that translate to how the overall electron hole states behave? I say that's just to emphasize the different values of the IPRs there. And what we can do also is calculate the energy resolved electron-electron and hole overlaps. So how localized are different electron states compared to each other? Now, when you compare electron 1 with electron 1 has 100%. Oh, sorry, by the way, if you look at the left-hand figure, hole 1 with hole 1 has 100% overlap. So you see a nice yellow stripe going up the picture there. And valence, so if we now go back to the conduction band, you can see that the white stripe going up is kind of whole electron N with electron N. But overall, that there's good overlap between all of the electron states, that they're generally well delocalized. However, if we go to the holes, near the valence band edge, you can see that the few lowest hole states have very little overlap with each other, and they tend to then have a weaker overlap with higher ones. And it's only when you get up to a much higher energy that you can see good overlap between different hole states. So there's clear transition from localized states near the valence band edge to delocalized holes at higher energy. And that can be seen again if we put in pictures here of what the different hole states look like as you go up, adding a different hole in each case, compared to the highest electron state, which is largely delocalized. So the atomistic calculations confirm highly localized holes, the electrons being perturbed continuum states. And then that, more detailed analysis in the paper shows that therefore the observed PL peak energy dependence on excitation energy is fully consistent both with the localization of the holes and with the energy scales over which things are happening. So, and I want to finish up by looking at the M-plane case, the non-polar indium gallium nitride quantum wells. And in this case, as we've indicated, again, measurements show that they are essentially random alloys with slight fluctuations. Despite being just random alloys, they're the supercell. I say if you do the experimental measurement, for these structures where the well width was about 2 nanometers, the measured PL energy, I need to check just down here, that's 2.8 eV, 3 eV, so the measured PL has a width of about a half width of about 150 MeV, and excuse me, that the blue points here are showing the average fluctuations across 75 cases, in this case, of the lowest electron state. And you can see the electron states do fluctuate, but nothing like as strongly again as the whole states shown by the red are fluctuating across different examples in this case. And if you then take the different calculated band edge energies there for the electrons and holes and put them into a distribution, you can see that the calculated width of the distribution of states is very close to that of observed experimentally. So the red line here is what we calculate theoretically for light that's polarized in one direction, and blue for light polarized in the other direction in the plane, and the dashed black line is the experiment. You can see that just the randomness present can pretty much accounts for the width of the experimental photoluminescence measurement. Again, if we do the calculations single particle calculations, ignoring electron-hole interactions. In this case, we again see the electron states in the M-plane quantum well having wave functions that look very similar to what you'd expect based on a continuum model, with the electrons distributed, well, partly trapped near the well with fluctuation, but extending over the whole region of the supercell we're looking at. Whereas the holes, again, because it's not the built-in field that's localizing the holes as much as the potential fluctuations, the holes again are highly localized. But in this case now, we turn on electron-hole interactions, the kind of Coulomb interaction. What we find is that when you turn on the Coulomb interaction, that leads to the lowest electron state starting to become localized around the hole state. And that exciton localization then is consistent with the measured exponential decay transients. Good. Just to, so I hope, just so I think that therefore the importance of including that if you include local atomistic effects, they account for a wide range of different aspects of what you observe in the electronic structure. Now, going back to the very beginning, I mentioned that one of the problems in 3-nitride LEDs is the droop, where as you go higher in drive current, the efficiency starts to degrade. And that's often attributed to Auger recombination, where an electron and hole, either side of the energy gap, instead of recombining to emit a photon, they recombine and excite another electron or hole to higher energy, thereby a recombination that conserves energy and momentum. Now, in an ideal structure, you would expect, actually, I think Auger is you expect to be not very likely, because of the requirement for conserving energy and momentum. But if you have built-in fields along the c direction, then that reduces the extent of the wave function in the z direction, as you've pointed out in the past cloud, and therefore increases the range of wave vectors k going into the lowest states. But also, on top of that, whole localization in the xy plane reduces, reduces the xy extent of the states, and therefore also increases the number of wave vectors k you need to put in there. And both of those effects can tend to break the strict requirements for conservation of energy and momentum, and therefore potentially underpinning Auger. And therefore, because of the disorder, I think, Auger, then it's the disorder introduced that Auger becomes an intrinsic process in in-GaN heterostructures. Now, and here's where I just step back to admire others who do the transport calculations, because in indium gallium nitride quantum LEDs, that have been discussed earlier and may come again later, a full LED simulation needs to include, obviously, the disorder that I mentioned, and also it needs to include tunneling, where we've seen that localization landscape does nicely deal with tunneling, and then in addition, it needs to deal with Auger recombination where particles collide, and unfortunately in this case perhaps the third particle may go flying up in the air rather than disappearing. I think I deliberately chose that picture as I think that's a red electron colliding with a green hole, but in any case I really should not have made any further reference to rugby today. My apologies to myself, but not to the English fans, I guess. Anyway, but to bring it all together, so just what I've been presenting is how the atomistic local atomistic disorder impacts on the electronic structure, and I think I believe that the empirical atomistic does give a good picture and understanding of what's happening on the length scales of relevance, but going beyond that to look at going to simulation, going back to my original 3 pictures of empiric, first principles, continuum and atomistic in the middle, that you really need to move towards the continuum, and hopefully that this does provide some of the underpinning to enable to do so. But overall, just to say that from my presentation, first of all, I think it's nice to be, when worrying about disorder, to say that yes, people who do first principles calculations, the results can sometimes still be misleading in the first principles calculations, and that you may need to go to larger length scales. Nevertheless, with those first principles calculations, they show that in the case of the 3 nitrides, localization of states in InGaN and in indium aluminium nitride, and then moving on to the empirical atomistic larger scale calculations, they provide strong support of the whole localization, while the electrons are well described per perturbed continuum model in general, and that then when you go beyond that to include Coulomb effects, that leads to it can lead from disorder to localization, localized excitons in the non-polar case, but not in the polar quantum well, and then that overall all of these factors are important when you come to simulating a full device, and therefore important to be able to deal with all of them in the full simulation. So I'll leave it there. Thank you.